Let's take a look at problem 18.8. An organ pipe open at both ends has a radius of 4 centimeters and a length of 6 meters. What is the frequency in hertz of the third harmonic? Assume the velocity of sound is 344 meters per second. So let's write that down. Velocity of sound is 344 meters per second, and that will be the velocity that we're dealing with in this problem. Now we have an organ pipe open at both ends. You know, if we had the fundamental frequency standing wave, that would correspond to a wave that looks something like this, where we had an antinode at one end and an antinode at the other end with a node in between. That would be the simplest configuration we could get to produce resonant sound. That means that the length of this tube for a fundamental is equal to 1/2 wavelength of the sound, because we're between an antinode and a successive antinode. So the wavelength for our fundamental would be twice the length of this tube, so that would be twice 6 meters, or 12 meters long. Note that the radius of this tube is not going to matter independent of the radius. Okay, so we want to find the frequency of the third harmonic. We got the wavelength of the first harmonic. The frequency of the first harmonic will be the velocity of sound divided by the wavelength of the first harmonic. 344 divided by 12 is 28.67. That's our fundamental frequency. And for an open-end pipe, our harmonics are going to equal n times our fundamental frequency. So our third harmonic will equal 3 times our fundamental frequency of 28.67, and that will give us a frequency of 86. So 86 hertz is the frequency of our third harmonic. If we were to look at this, we would have a antinode at this end, a node, another node, another node, and another antinode. So in this particular case, for the third harmonic, the length is equal to 3/2 the wavelength. A quarter here, a half here, quarter here. 3/2 wavelengths. Frequency is 3 times higher, and the length, the wavelength is 1/3 as much.